Hello everybody. You're in the PyVista tutorial. If you're in the wrong room, you can leave. Our feelings won't be hurt. I'm Bane Sullivan, and I'm joined today by Ketsu and Kevin. So we're going to talk about 3D visualization, 3D data analytics. I'll let
Hi, okay, so I'm working as an engineer, and my major is physical simulation, and I usually use PyVista when I'm visualizing the result of the physical simulation, and I'm co-developer using PyVista. Thank you.
Hi everyone, I'm Kevin Tile. I am a meteorologist and IT manager in my department, which is Department of Atmospheric and Environmental Sciences at the University of Albany. I teach a couple of Python data analysis and visualization classes for our students. And I've been at PyVista tutorial a couple times, so I might be able to help some of you folks. Looking forward to it.
Thanks, y'all. So yeah, Kevin's joining us to help today. We're a little short-handed, so if you have issues, raise your hand, and Tetsu, Kevin, and I are all happy to come around and just directly help you. Oh, I do have to introduce myself. So my name's Bane Sullivan. I'm a software engineer. I have a background in geophysics and hydrology, and today I work for a mining company called Cobalt Metals, and yeah, I sort of used to be a scientist, used to do geophysics and hydrology, found that there just wasn't any good free tooling for 3D visualization. It was like, go use some commercial package that was just really, really expensive and not approachable while I was doing research. And so I started working on making little scripts and doing some open source work for 3D visualization, and found I just liked software engineering a lot more than science. And so here I am. Cool, so I'll get started, I guess. So a few logistical things. All of the tutorial content is hosted on a website. So this is our 4th year hosting this tutorial. Each year it kind of evolves a bit and we add new sections, new material, but it's all at tutorial.pyvista.org. And so everything we go over today is on that website. I'm just going to have that website pulled up and scrolling through some of the pages with you all, as well as interacting with some Jupyter notebooks. We had some issues getting the Nabari computing environment to work fully for this tutorial this time around. So I want to get a raise of hands. Who is planning on using Nabari? Sweet. Okay, so yeah, if you can run locally, so I saw no raised hands, so I'm going to assume everybody is able to pip install or conda install packages on their own machines. I saw a head shaking no. Okay, I will call you out to make sure everybody is up and running. But yeah, okay, that's excellent. So that's really, really good news. If you are running locally, this will work wonderfully. But we'll have like a 15 minutes or 10 minutes, however long it takes. We will go around, make sure everybody has everything installed, it's working properly. Just the way 3D visualization workshops go, it always takes more time than we plan for. So yeah, I guess I'll give a little backbone or a backstory to PyVista and the software we're working with, and then I'll put the mic down and we'll just make sure everybody's able to load the first notebook, know where you can get the notebook and all that stuff. So PyVista, I want to talk about a little bit of the tech stack that PyVista is built on, and it's called VTK, or the Visualization Toolkit. So PyVista is this thin wrapper layer on top of this 30-year-old, nearly 30-year-old visualization library called the Visualization Toolkit VTK. It truly is the backbone of scientific visualization today. It has millions of lines of code. It has millions of downloads annually from Kitware's web servers. Kitware is the company who's built Visualization Toolkit. And disclaimer, I used to work at Kitware and no longer do. But it has just global adoption for doing scientific 3D visualization. It really is some of the best software around for it. However, it's 30 years old, it's written in C++, and it's really, really tough to use. And so what we really set out to do with PyVista was provide a more modern Pythonic API for using VTK and leveraging that really powerful visualization framework. And so on the left, and this code snippet's on the website somewhere, we'll probably run into it in a little bit, but I want to drive home that there's really just two conceptual things happening here. And the conceptual part's more clear on the right with PyVista, where we want to load some data, like, read some file. And so on the VTK side, we say, we instantiate this reader class, we set a file name of bunny.stl, and so an STL file is just like a triangulated mesh format, and then we go through all these things of setting input and output connections, making an actor, a mapper, a render window interactor, all of this stuff. Like, if you're a hydrologist or you're a meteorologist, you're probably lost and your eyes are glossing over, you just don't care. And so the whole purpose of PyVista was to simplify that and abstract it and make it so it's a lot more approachable. So if you want to load something, you just get a read function like pandas.readCSV. And so we have a PyVista read function where you just pass a file name and some options for controlling how it's read, and then you get back some sort of object. In the case of pandas, it would be a data frame, and like on a pandas data frame, you say df.plot, and you can plot an X column and a Y column. And same thing in PyVista, you just say mesh.plot, and you get a 3D visualization of your data set. And so this is really this captures sort of the spirit of PyVista, is our goal to just make all of that complicated nuance behind 3D visualization and computer graphics completely transparent, and make conceptual tasks just one line of code. So if you want to read something, one line of code. You want to plot something, one line of code. You want to transform something, like produce contours, one line of code. While also being really, really flexible. And so, our guiding principles here are really just to let people work naturally within their own ecosystems, use NumPy arrays, work with pandas data frames, and reduce all of that boilerplate code that we see on the left here of setting connections and actors and mappers and interactors and all of that stuff. So reducing that boilerplate and then just providing immediate intuitive access to the visualization. So, so it's all about minimalism. We really strive to have excellent documentation. So today you're going to be going through our tutorial website, which is a standalone website. We also have a much more comprehensive documentation website at docs.pyvista.org. And really, it's just the message here is PyVista. It's built for any Python developer or domain scientist, anyone using Python who wants their 3D visualization to be easy. They just expect that their 3D visualization toolkit looks and operates the same as all their other data analysis toolkits. And so if you're coming from the Python data science world, you're using Matplotlib, Pandas, Plotly, all of these really great and fantastic, easy to use libraries. Our goal is to fit right in and provide something powerful for 3D visualization. Okay, so who's PyVista for? It really is for anyone, and I changed this line a little bit today, anyone who wants to work with 3D data using Python. So more than just 3D visualization. If you want to work with any sort of 3D spatial data, we think PyVista is the right library for you because we provide data structures for interacting with that data, transforming that data, and performing analysis on that data in addition to all of the rich 3D visualization features. Okay, so we are going to make sure everybody's found the website. We're going to get everybody installed, and I'm going to have you all pull up the first notebook. Okay, so I'm going to put this here. And let me know if I'm not talking into the mic and you can't hear me. So the tutorial website, again, it's tutorial.pyvista.org. Everyone's found it, hopefully. Now, on the getting started, so I'll zoom in a little bit, make sure that I can see. There's a getting started section, and in here we have the installation instructions. So if you're using pip, it's going to be pip install, and then oftentimes you need to put in quotes, but PyVista bracket all, and that will make sure you get all of the additional community dependencies that we need for some of the examples we're going to run today, and for making sure this works seamlessly in Jupyter. And then, of course, you're going to need Jupyter Lab. And for Conda, there's a tab there, and you can just copy these commands, and it will install all the dependencies. So now that's installing in your virtual environment. And to find the notebooks, so if you're on this website, you go to the PyVista tutorial section right here on the sidebar, and then this big blue button right here at the top, this will download a zip folder of all of the notebooks for today. And you'll want to open up that folder in Jupyter Lab. So I'm gonna just come around the room and we'll make sure everybody is able to spin up a virtual environment, install PyVista, open up these notebooks in Jupyter Lab, and then we'll go to the very first notebook, which is in the folder, and let me zoom in a little bit. So, is that, yeah. It's in 00 intro, and then there'll be this a basic notebook. So I'm gonna just start coming around the room, and we'll get a show of hands who isn't up and running yet, and we'll try to help. All right, everybody. I walked around a bit and I saw a lot of you going ahead and running this first notebook. So this first notebook is sort of our version of a hello world in PyVista. We're gonna talk about what all these things are doing and what object type they're returning, how you can work with those. But this is just a quick notebook to really, well, look at me, I got in here now. So it was working for me just a minute ago, cool. So this is our hello world. The very, very sort of top level thing. We import PyVista as PV in all of our notebooks, just like you might import NumPy as NP. So you'll see that everywhere. And then under the PyVista PV namespace is all kinds of ways to produce different geometric objects, ways of instantiating different data types, and ways of, and then there's this big PyVista.plotter class. Those are sort of the main ways you're going to use the PyVista library. And then, of course, once you produce some sort of data object, it's going to return what we call a mesh. We have a whole section in a moment dedicated to what a mesh is and how you can work with that. So this notebook, it's just creating a few basic geometric types, cylinders, arrows, planes, line boxes, polygons, all of that stuff, and just returning these objects that represent those. And each one of these variables here are what we call in PyVista just a mesh. They are, so if we just print out the first one, so it shows it's a polydata mesh. It's got 400 points, and it's got some other metadata associated with it. And really, we just want you to run this notebook and make sure everyone has a 3D visualization up and running in their notebook. They can interact with it. They can kind of wiggle some of these geometries around. I think everyone's gotten to this point, so I'm going to go ahead and we're going to dive into the next section. But definitely raise your hand if you didn't get a 3D visualization under that notebook. Okay.
More questions?
Okay. So I'm going to go through a little bit of the history. Everyone's up and running, so I'm feeling good. Or we have a few hiccups, but I'm feeling pretty good that everyone's up and running. I want to give a little more history on the project, just call out some of our contributors and things, and then I'm going to jump into, and you can follow along. So actually, please pull up the website and look at these sections with me. There's lots of links you can click on. You can see galleries of our examples, learn about other contributors, the VTK, the visualization toolkit, software we rely on. But after this, then I'm going to jump into this basic usage section. So I want to call out, because it is really important, that PyVista is built on top of VTK. None of this would be possible without all of the extraordinary work done by Kitware and done by the VTK community. PyVista, our goal was really just to abstract VTK and make it as approachable to scientists, engineers, and developers who want to leverage it. And so I want to talk about why Alex Kaszynski and I started PyVista. And back in 2016, Alex actually got working on some commercial software he was building called FE-Morph. It's like mesh, I always mess this up, but it's like you sort of metamorphize these mesh geometries, and so he has these ways of warping the geometry of meshes to respond to stress and strain conditions and things like that. And he's probably going to think I just butchered that, but he really needed a lot of 3D visualization in that work because dealing with 3D geometries, he needed to visualize things. And he was using the visualization toolkit VTK, but found himself consistently sort of repeating a lot of the same patterns, going through that boilerplate in the VTK code that I showed earlier time and time again, and just started writing some scripts to automate and just create a few Python functions that do a lot of the same boilerplate over and over again. And then, I think he found himself realizing that working with the data structures that VTK provides just wasn't very intuitive. It didn't have direct array access, and so that way there was no sharing of memory between the NumPy arrays that you're processing in Python and the underlying C arrays that we're dealing with in VTK, and started wrapping some of the data structures. And then I shortly joined the project because I was running into the exact same issues, but I was a graduate student at the time working on geophysical modeling, inversion, those sorts of things, and just found myself repeating a lot of the same stuff. We needed to be able to reproducibly generate 3D figures in our research. And a lot of the graphical user interface software, desktop software just wasn't cutting it because we couldn't change our models and rerun a simulation and then reproducibly create the same 3D figure with the same camera angle and lighting and all of that every time we wanted to change our model or change our science. And so I started writing a lot of the same scripts for automating these boilerplate tasks in VTK. And I also needed to directly manipulate the underlying arrays that were in our mesh data structures in VTK. And so I joined the project in 2017 or 2018, I forget. And Alex just had his code on GitHub. I found it by chance and was like, oh my gosh, he's doing the exact same thing I'm doing. We both started committing to the same repo. We were sort of both doing a lot of the same stuff, but also a lot of different stuff, very complementary work, and it just sort of really came together quite nicely. And we had our first release of PyVista in 2019, I think, and we shortly after published a paper in the Journal of Open Source Software. This is just a high-level overview of basically our philosophy, the goal behind PyVista, and what we think it enables for research. So please definitely check it out. And so as of July 2025, we have, I think, over 190 different contributors to the software beyond Alex, Tetsuo, myself, and 3,000 stars on GitHub. If you're following along, please go on GitHub, give us a star. It actually goes a long way in helping our sort of exposure and visibility, so give us a star. If at the end you don't like our tutorial, you can always unstar, but please don't. And the other thing we're really proud of is it's used by thousands. I think GitHub's tracking us right over 4,000 other libraries, examples, and repositories on GitHub, where just a lot of people from all walks of science, I guess, rather than walks of life. So all kinds of domains from the world that I come from in geophysical and subsurface modeling to the world that Alex Kaszynski comes from, which is in mechanical engineering and aeronautical engineering. Tetsu is a machine learning engineer. There's all kinds of people using PyVista for all kinds of different domains because a lot of the same challenges arise for 3D visualization across all these domains. And so Alex Kaszynski and I are the creators of PyVista. Tetsu is a core maintainer and has done a lot of work over the years, joined the project not long after Alex and I published it. Andres Deek has put a substantial amount of work and effort into building PyVista out, and same with Matthew Flam, user 27182, and many, many others. So please go look at our contributor graph, see all the excellent people who have greatly expanded and made PyVista truly a community effort. And so Alex and I, both of our roles in the project have sort of ebbed and flowed through times as our careers have evolved, and different people have stepped up to lead the project. So with that, I kind of want to encourage all of you, if you've never opened a pull request or contributed code to open source, like maybe consider it with PyVista, because we've put a lot of work into trying to lower that barrier to entry. And if you want a new feature for PyVista or in this library, like please feel free to contribute, and those contributions could be actual code or they could be documentation examples. In my opinion, they're equally important because no one will know how to use the software without good documentation examples. So definitely, please consider it if you're excited about open source. So yeah, I went over this example earlier. The whole spirit of PyVista is just trying to take that BTK code and make it really, really straightforward. And yeah, so and we have a few other examples with that, but let's jump into the tutorial content. So we did the hello world where we spun around all the different geometries. Let's go to now, I'm going to jump ahead into the basic usage section. And we're going to talk about like your standard your standard ways of interacting with PyVista and how people typically use PyVista. And so I'm going to kind of overview a lot in here, and you're probably going to have a lot of questions about what data structures are and things like that, but we're going to get to some of that later, but do ask questions as they come up. Please feel free to raise your hand at any time. So yeah, there's two main ways of getting your data into PyVista and into our data structures. The first and likely easiest is just loading a file. I made the example earlier of you have a CSV file or a Parquet file, and Pandas you say read, and then it gives you back a data frame. We've tried to do the same thing in PyVista. So there's a PyVista read function. You just pass it a file name of a common 3D format. We have a lot of different file formats that we support, and if you're on this page following with me, you can click on this and open up many of the different readers and file formats that we support. My best advice is just to pass a file name to that pyvista.read function and see if it works or not. Oftentimes it will. Yes?
If you're writing a file, is there a preferred format?
That's a good question. It depends on your goals and like what you want to do with that file once you write it. And so if you're just trying to save a file and reopen it to work with PyVista again, I recommend using .vtk as the extension. And so on all of our data structures, you can just say mesh.save, name of file .vtk. That's going to be your best option for file format for saving, closing your process, reloading. But of course, there's many other formats we support exporting to, like if you want to take your work here and put it in commercial software or some other desktop software, you might want to use an OBJ file, STL, PLY. There's lots of options, but I think your best bet is .vtk. Okay, so yeah, check out the compatible formats. We use a popular library called Mesh.io for a lot of our file I/O. So if you Google Python Mesh.io, it will show a really popular open source library that does sort of file I/O for different mesh types, and we leverage that. So any format supported by Mesh.io, we also support. But the other way of creating a mesh object and loading data into PyVista is actually like you have a bunch of NumPy arrays and you want to create your point cloud, you want to create your geometry manually. We'll get into a little bit of that later, but I'm kind of just going to focus on loading data from files because it's much simpler for the tutorial today. And what's really nice is we have a lot of example files that come sort of baked in with PyVista. And so we have this from PyVista import examples module, and in there you can just say examples.download_, and there's a whole bunch of options. And so this one, download saddle surface, will give you this sort of saddle looking surface, but you can tab complete on examples.download_, and I think like over 100, maybe more example files will pull up, and all that's doing is well, one, it downloads a file from one of our other repositories on GitHub, downloads that file, and it just calls PyVista read on that file. That's all it's doing. And so there's nothing too special about these example things other than they're just loading example files. And so once you load something, whether it's through PyVista read or it's one of these examples, it returns what we call a mesh in PyVista. And then you can just say .plot, and you can immediately see that result, and you can interact with the visualization. And that .plot function is, you can configure all kinds of keyword arguments, such as show edges, that show the edges of the geometry. You can set the color to different things. You have a lot of flexibility and control. This .plot method is just a convenience method to see one mesh at a time. Yeah, and so I want to go over, and actually I should probably get off the website, and I'm going to open the notebook with you all. So if you're opening the notebooks, this is in 01 Basic, and I probably should have gone over this. We've laid all this out, so there's a notebook that has sort of the lesson overview. This is what I'm going through, and then there's a folder of different exercises that we're going to have you do after I'm done with the lesson. And then if you don't feel like filling in the blank or wherever we sort of left the task for you, there's solutions that just have the answers. And so if you just want to skip to the solution notebook and run through that, understand it, interact with visualizations, that's more than fine. So I'm opening up this, so again, 01 Basic, and then this A lesson Basic. So I'm just going to run through here, and so what I have with this download surface, or download saddle surface, I have a polydata mesh object. It's got 2,600 points, it's got 5,000 cells, and then I can just say dataset.plot, right? And I can throw other options at it. And so I can just say, I can shift tab and see all the available options for when I'm plotting. I can change the color. My favorite would be maroon, and we get a nice deep red surface. And there's all kinds of options we can control here. And again, this .plot, it's just a convenience method to see a single data set at a time, quickly introspect it, and just take a look at what your data looks like. Let's look at some other examples. So this download frog, this is a volumetric data set. So this first one I showed, it's just a 2D surface. If I toggle the edges on here, that looks horrendous on the display. So I'll go back to like a whitish color. Sorry. Where am I? Whoops. So what happens when you run out of order? And then I can turn on my edges with this button. It's just this triangulated surface, just a whole bunch of triangles. It's a 2D geometry, right? But let's download this other one, this download frog. This is returning now an image data object, and this has some dimensionality to it that the surface didn't. And so it's got 500 X component, so cells in the X direction, it's got 400 in the Y and another 100 in the Z direction. So it's creating an actual full 3D volume or distribution of data. And if we just do a dot plot on this, we can pass in this volume option. And if you say volume equals true, it's going to turn on a volume rendering mode. And so we can see actually what is inside the data. Because if I don't do that, and I just say dot plot, what we get is just, it's a big grid. We just see the exterior surface of it, but we want to see inside of it. We want to understand the distribution of our data inside. And so you can turn on this volume rendering mode. So volume equals true, and then you can see the actual data inside that volume. And this is I think a scan, like an X-ray scan of a frog. And so this frog is inside that volume of data. If this file is missing, the iron pot file, you can click this link, and it should, you can go to GitHub and download it with that link, and I will just place that here. But again, this is just showing the PyVista read function. If you have a file, just throw it at the read function and see if it's supported. And so I just downloaded it. I'm going to play it right here. I'm going to try again, and there we go. So this iron pot, similarly, it's image data. It has some Z dimensionalities, 68 by 68 by 68. And if I do the same volume plotting, we're going to see now, okay, it's got a whole distribution of data inside of the 3D volume. Cool. So that's the basics of you have some data, you can read it in, you get this mesh object back, and then you can just start plotting it. You can start seeing in 3D, looking at it, and start working with it. So I want to now take a moment for you all to go through these exercise notebooks and see how far we get. I think the, I'm trying to remember. Yeah, I'm curious, has everyone had a chance to go into this already? Have you jumped ahead or no? Okay. Yep, so inside O1 Basic and then Exercises is the folder. There's one Jupyter notebook in there. And let's have everybody go through that and just run through it and see what all these look like. And a challenge I'd like for you all, or I guess, yeah, the exercises are outlined here. And so I'll just let you all do that and we'll reconvene in a couple minutes. Yes.
Just curious, like, I guess what attributes of the objects, like, can you see the raw data? Maybe something having a problem kind of like understanding some of the point cloud data versus like the written data and kind of like small structure.
Yeah. So in the next section we're going to go through, which is what is a mesh. I'm going to dive all into that. And all about how we create geometry and how we can put data on that geometry and different ways you can do that. So yeah, we'll get to that in a moment. And yeah.
And is the kernel kind of dying on here, or is it just getting stuck? environment?
The environment.
Can you run Windows?
I'll see something.
Has anyone who's running Windows gotten things to work properly? Just like nothing gets, it's like no widget. Do you have any luck?
Kind of.
Yeah, I did it with. Just mixing different compounds, especially if it is available on Canada. I usually use PIP only if the package doesn't exist on Canada or.
Yeah, I'm the opposite way.
Yeah. No. She added a couple extra packages for pepper. Things stopped working. She did it, she's weird, just calling me,
Oh, sure.
Yeah.
Yeah, we may just get you set up on
Okay, so we're just ironing out some issues with a few people, but I was sneaking in everybody's screens, and it looks like a lot of you are jumping ahead, which I love. I saw some cool graphics on some of your screens. So, did anyone, if I go back to this exercise, did anyone find, because I think the first task was just like find an example, download, did someone find one that was cool? You want to shout it out and tell me what it was?
It was a shark.
Sharks are always cool.
Shark 3D printer.
Yeah. Anyone else find anything particularly interesting?
The brain.
The brain scan? Yeah, those are pretty cool. And did you do volume rendering with it?
Yeah, it's hard to get just, I couldn't get just the brain without the skull.
Yeah, you have to choose. So you'll have to run some filters, which we'll talk about in a little bit, to extract or cut out all the air in that scan that you don't care about. So I think, yeah, examples, download brain. Anyone else? Did anyone try to load their own file? 2 people, 3 people. Oh, awesome. Did it go well? Okay. What kind of data do you have? All of you? Any of you?
I've worked with the elevation of potentially an array, just run X-ray, just ran a point and figure out how to scale it, scale orders.
Yeah.
Spans large orders of magnitude, so just trying to scale that.
Yeah. So you're an X-ray person. You use X-ray a lot.
Yeah.
Okay. Well, there's a lot of community tools in that space for you. So pull me aside at some point. We can talk about it. Or if others are interested, we can do that later. What about you? You did something? Sweet. Cool. Just a random file. Great. Cool. Yeah. So. Okay, I just want to see the brain one because it's cool. And then we'll jump on to the next section where we're going to learn about the data structures that we have. Yeah, and so this brain one, this is a cool example. And I think if you go look at our example gallery on the main documentation website, we have one probably for contouring or iso surface, iso volume. If you search for that in the example gallery, you'll see the same brain example where I think it does show the brain itself. So feel free to go find that. But yeah, let's jump on to the next section, which is all about what a mesh is. Okay. So we're going to talk about, first I'm going to talk about just the underlying structure of a mesh. I recommend, if you have some time on your own, or if you want to read a little bit while I'm talking, to go to the tutorial site again, go to this What is a Mesh page and read through some of this. And what's really great is this is a condensed version of our main guide on like our data structures in PyVista and what a mesh is. So definitely click on this, go learn about the structure. I think there's actually some better graphics on our main documentation site that really try to drive home the different data types we have in PyVista, the difference between what a point is, a cell is, all that jazz. But what I'm going to go over right now is the basic structure. What is a point and what is a cell? Basically, a cell is how you connect many points to produce some sort of connectivity or geometry to represent things like a surface, a volume, all of that, and then how you can put data arrays, the actual scientific data you care about, onto that structure and visualize it. And so often, many of us probably don't care too much about our structure, so much as we really care about the numerical data that lives on that structure. So if you're doing, in my case, like subsurface modeling, I care about knowing the density in the subsurface. And so I want to plot the density as an array, as a color mapped value on a big grid, and then do things like thresholding or iso voluming it. Cool, so let's go to this Jupyter notebook and run through it together. So I'm in, again, this is o2_mesh, and then the lesson overview notebook. And then I'll have you all go through some of the exercises on your own. Okay, so let's start with sort of the most basic of 3D data, and that's a point cloud. We can create a point cloud with just some random array data. So I'm going to assume everybody in the room has used NumPy before, and the idea of just calling np.random.rand with some shape, and creating a 2D array, that's hopefully a familiar concept for everybody. And so here we're just creating 100 rows and 3 columns. And so this is like if you have a spreadsheet or a table of X, Y, and Z coordinates. And I'm just looking at the first view, and we can just pass those points directly to a PyVista type called polydata. And so polydata is a mesh type in PyVista that's used to represent 0-dimensional, 1-dimensional, and even 2-dimensional geometries. And so that might be a lot to unpack. So 0-dimensional geometry is a point cloud because there's no connectivity between your points. If I just look at my point cloud, it's, oops. So I instantiate my polydata object from those NumPy points arrays. So I still, I get 100 points and 100 cells because there's a cell for every single point, and it's a 0 dimensionality because when I plot this, I just get, a point cloud. These points don't have any connectivity to the other points in the point cloud. And so while we call this in PyVista a mesh, that's really just a convenience term for us because we worked really hard to sort of just make this simple for everybody. So whether you have a point cloud, a volume, a grid, a surface, we just call them meshes in PyVista. And just to make it easy to work with and provide a really consistent API, so that way it kind of looks the same. If you're dealing with a point cloud or you're dealing with a grid or a full volume, it should all look the same, and we kind of just call everything a mesh. But I want to talk about dimensionality. So this point cloud, it's just 0-dimensional. The points aren't connected to each other. If we started connecting the points together, if we just connected one point with another, that now is a 1-dimensional geometry because we have just a line between 2 points. But if we added a third point in there, then it becomes a 2D dimensionality. So that would form a triangle if you have 3 points. And so polydata is a type in PyVista that's used to represent 0, 1, and 2D data sets. As we get into 3D geometries, that's where things get a little more complicated or a little more fun. And we'll do that in a moment. So it's important to note that beyond point clouds, every mesh type is going to have some sort of connectivity between the points. And so here's another example from our examples module, load hexbeam. And what this does is it creates a grid of a bunch of voxels. And there's a little rendering artifact on my computer where it adds in this extra diagonal. It's kind of faded, ignore that. These are all voxels. And what it's doing is it's basically taking and saying, hey, for any given 8 points, connect them and create a cube. And that is the connectivity, or that's the geometry of my mesh. And so now we have some 3D geometry here. And so every mesh is going to have some points and often some cells. And those cells, again, 0, 1, 2, and 3 dimensionality. And so I want to show, so that's connecting 8 points together to create a voxel, and then many of those voxels creating a whole mesh, and so we get this big grid. And we can also do this for a triangulated surface. And so here's another example, the bunny. And so this is just a triangulated surface mesh. So there's no actual volume information here. If I zoom in, I can kind of zoom in past it, and I can look inside of it. There's no underlying 3D structure to this. It's just a 2D surface moving, undulating in 3D space. And it consists of a bunch of triangles. Cool, so I want to talk a little bit more about these cells. The cell, it connects, it really forms the topology of the mesh, and it connects the points to create some sort of meaningful structure. It's really quite necessary if you want to do, if you want to have any sort of data that lives on your data structures. So I'm going to take that hex beam example that I just showed. We're going to extract a single cell. And so this one, I just say mesh.getCell, and I can say just in cells -1, so I just get the last one. This is a hexahedron, and really, actually, it should have been voxels, so maybe that's why it has that weird rendering artifact of that extra triangle. But, and we can just run this cell, and we plot it, and we can see it. So it's just that extra cube right here on the end. And so it's just defining, saying, hey, all those 8 points, let's connect them together and make a voxel. Now, what's interesting that I want to show is if we go to mesh, and I just show this output menu book. So I have an unstructured grid, and I have 99 points and 40 cells. I'm curious, why people think there's such a discrepancy in that number. There's nearly 100 points in this mesh, but only half as many cells. Does that make sense to everybody? I'm curious if someone can explain why. Exactly. There's a ton of shared points. That's the real key there. And so these, like, if I zoom in right here, these 2 voxels, they have these 4 points shared between them. And that's exactly why. And so cells can oftentimes, very often, do share those points. Yeah, great. Okay, so let's talk about attributes now. So we can have, so attributes are basically any data array, any sort of numerical information that you want to live on the geometry of your mesh. So there's 2 modes of this, and this follows the 2 sort of concepts in defining our mesh, the points and the cells. You can have point data, and point data, what these do is they live on the nodes, on those vertices of the mesh. And so if I go and I plot this, what we have here is, let's actually look at this code a little bit. Let me zoom in and make sure we can read that. So we can access the different data arrays on our mesh with this .point_data. It'll be the same for .cell_data. And you can kind of treat it like a dictionary of data arrays. You can index it kind of like a dictionary, or kind of like how you look up a column in a pandas data frame. And this, it has to have the same length as the number of points in your mesh. And so there's this one-to-one mapping as you go down this array of values to the vertices of your mesh. And so that's why I say np.arange mesh.number of points. It has to be one-to-one. And so all I've done here is I've just iterated over all the points and basically just given them a numerical value of their index. And then I can plot, I can say mesh.plot, and I can say, okay, view these scalars, my point values, and we'll show the edges, and this is what we get. Now, I'm curious if anyone can guess as why there's sort of a gradient in the coloring here. Not quite what I'm looking for. And I heard someone say shadows, and that's also not quite, that will lead to some coloring differences and things, but here. Okay. Yes, that's important. Maybe I'm doing a bad job of asking my question. So what I want to get at is, like, we look at a single cell, we see like quite a strong gradient. And that's because the actual data is defined at the vertices, and so we have like very, very discrete points of data, and we have to interpolate between them. And so across these cell faces, I only have data like right here at this vertex, and at this vertex, and this one, but we don't have any data for the cell, for that whole face. And so what we have to do is we look at all of the data at all the points on that cell, and we interpolate, and that's how these triangles on that surface get colored. And so that's why there's a bit of a gradient. And so yeah, how in this case, the ordering is a little bit weird because we have like some lower index cells on both ends, and the ordering doesn't necessarily make as much visual sense. But I really wanted to call it out because with cell data, we do have like a constant value across the whole cell. And so same thing, cell_data, we can index it like a dictionary. Again, it has to have the same length as the number of cells in the mesh, so mesh.ncells. And let's plot this one. And here, this time we don't have that gradient. We have a solid color for every single voxel. And that's because the entire cell, that entire voxel, is assigned a constant value of the value in that numerical array. Cool. Any questions on that distinction? Okay. So, and now there's one more type of data you can associate with a mesh, and this one's a bit of a wild card. Well, actually, I'm getting ahead of myself. Let's take a look at this little snippet right here, because it really highlights that difference of, if you zoom in, you can see point data, we have that interpolation where as I move through the voxel, we have to interpolate to the value or the color of the next point. And then for cell data, we have discrete values or colors for each entire cell face. And so if you zoom in on this example on your own computer, you can see that sort of, depending on your eyes, whether it might be a stark difference or subtle. Often cases, as you move into real world data sets and large data sets, it's gonna start to matter a lot less. It kind of depends on your domain and what you're doing. If you're doing certain types of simulations and things, it's gonna be very important to you. But visually speaking, for higher resolution data, you're not gonna see much of a difference between cell and point data, whether or not the colors get interpreted when you're really zoomed out on a high resolution mesh. But it is something, like if it is important to you, it's probably gonna be really important to you. No, there's really no performance difference between the two. And there's different ways of handling that interpolation between when you're doing the point data and whether or not you're interpolating the numerical value across that face and then color mapping it, or if you're color mapping at those points and interpreting in the color space. So you have actually two options there. And so that can be really important. And there's a great example on our documentation site I can point us to in a second.
So those would be performance implications, like what if you're sharing a whole lot of points, you've got significantly more cell that's not going to performance.
I've never dealt with a performance implication from it. I don't have like a technical reason for you or anything, but I'll just say from my own experience, I've never had a performance issue with that difference. Okay, so, and then there's one more type of array or type of information you can associate with a mesh, and this one's called field data. And this is just kind of a wild card. It's a way of associating any arbitrary length array with your mesh. And so there's some community packages like, I think GeoVista does this. So GeoVista is a cartographic rendering extension to PyVista. It's its own community package that does all kinds of cartographic map rendering on a globe in 3D with PyVista. And what's often really important, they want to know like the CRS or other metadata that's associated. So CRS is like your geospatial coordinate system, and they want to know it. They want to track that string of characters that define the CRS with the mesh. And so that's not something that lives on the points or lives on the cells. It's just arbitrary metadata, arbitrary arrays of information that are associated with it. And so here we can just assign an array of foo and bar, any strings, any numerical data, anything you want can go in this field data, but you cannot color map or render with field data. This is just basically for metadata only. But it's really useful if you just want to track additional metadata with your data sets. Okay.
Render in any way, just attaching it, save it to a VTK file.
Correct. Yeah, and that's a good point. It will probably only stay with it if you save it to a VTK file. Many other formats probably don't support the sort of field data arbitrary information. But yeah, it will just stay with it. And so that way, as you pass your data along to different filters, like if you want to contour a volume and do things, as you move your data through that pipeline of operations, that field data, that metadata will stick with it.
So the cell data and the point data, that always has to be as an array type.
Yes.
Point data, is that still true, or could that be like a dot array?
It does have to be an array. So all these have to be NumPy arrays. So cell data, point data, field data, they do all have to be NumPy arrays. What's great about NumPy arrays is you can do like kind of an arbitrary object-y type, but we'll have a limited subset of what's supported in PyVista for that. And so basically strings and numerical value. Okay. Yeah, and this is just another example of cell data and point data. There is, I guess, how are we doing on time? It is almost 3 o'clock. Let's go through these exercises. So I'd love for you all to just go into that exercises directory and go through some of these and ask questions. We'll be around the room, and then I'm gonna convene with Tetsu and see what we're gonna do next. Okay, so I want to drive home these exercises. There's the exercise directory, and then there's the solutions. And so there's missing code in those notebooks that are under the exercises directory. So you're gonna have to fill in some extra code. And if you run into errors, you're likely just missing some code. And I'll call out this one that was for adding vectors to your data set. What we wanted to see is index so point underscore cloud is the mesh object that you have, and then you created these vectors. You created some vectors as NumPy, a 2D array of X, Y, and Z vectors, and then just brackets, like a dictionary, call it vectors because down here we call it vectors. And if you just pass that NumPy array around, then you'll get your 3D visualization of the vector field. So you just had to add that array data onto your mesh. And do no shame in just jumping to your solutions. It is a lot easier, and especially if you want to understand the code.
Yeah. Yeah.
Yeah, so some interesting questions coming up. So just some like conceptual things. I talked about cells and voxels and stuff like that. So a voxel, it's a type of cell. Cell is just a generic term. A triangle could be a cell, a hexahedron, a pyramid shape could be a cell. There's a whole bunch of cells, and our documentation probably has a rich guide of this. And so a cell is just a single unit. It's sort of that primitive. And a mesh would be a group of cells. And so if you have many, many cells, that now becomes a mesh. And the other interesting question was around adding multiple data arrays. So in this first exercise, where you created a point cloud, and let me hide this sidebar so it's legible, and we just plot it, and we get that point cloud, and we wanted to add some data. And so here we did add an elevation array where we take the z component of the points and just add it as another array using that dictionary point data syntax. So one thing, I think in the lesson I showed that it would say like your mesh object, and you'd say dot point underscore data to give it point data, or you'd say dot cell underscore data to give it cell data. We've made it a little more convenient, so you can just use brackets on the mesh, and it will look at the length of the array, because I said earlier, your data has to be the same length of either the number of points or the number of cells. And so it looks at the length and then assigns it appropriately, so it's just a little bit shorter, so that way you don't have to mentally keep track of that. So you can do that, and then you can plot. And this plot function, it just immediately showed that elevation data, right? And that's because we just look at the mesh and we say, hey, is there any scalar data available There is a whole notion of activating a scalar field on a mesh and stuff, where you can choose which field, but so it just looks for one and grabs the first one and color maps it, and so that's why it does all this color mapping without specifying any options. But if I added some other data and I said point cloud, you know, Bane equals, and let's do the points 0 this time for the x component, and I do points, there we go, and then I plot this, again, it's still plotting that elevation data, and so I can add another argument here, which is scalars, and I can say the name of the one I just added, Bane, and then that will plot the other data array. And so you can have a whole bunch of arrays on a mesh, and then you can use these parameters to control which one you're color mapping by. Cool. Any questions coming up as you're going through? So I'm going to jump over to the C, creating a uniform grid notebook, and let's go through this. There's some questions about why you might do n versus n plus 1 on the number of points in order to assign cell data and point data. So I'm just going to run through this. What I've done here is I've got a NumPy array. It's a 3D array here. That's this first bit where I'm taking the lin space from, sorry, I just want to make sure I don't misspeak. Yeah, 0 to 10. That's a lot of points. Okay, so I'm taking a lin space of 0 to 10 and then chopping it up into 1,000. So I get a length 1,000 array of values between 0 and 10. And then I'm going to reshape it into 20 by 5 by 10. So if you multiply all those together, that equals 1,000. So that's the dimensions now of our 3D grid. And so that's what we get, 20 by 5 by 10. We can create an object type in PyVista called image data. What we can do is you can say, there's actually a number of ways to make this object a little easier, but we're giving the hard way to do it here, just to drive home the dimensionality of the data. So we can instantiate the PyVista image data class to represent this. And then what we need to do is we need to set the dimensions of that image data. And so depending on if we want that, that length 1,000 array to live on the points or the cells of the grid, this is going to vary. And so if we want this to be on the cells, what we need to do is set the dimensions to be that n plus 1. And this is really where I need a whiteboard to draw this, but if you have 2 cells, or sorry, 2 points, and you have 1 cell, so that's your n is 2 in that case, and your cells are just 1, right? And so now do that in 2D. And so if you have 4 points, that's still 1 cell, but 4 points. And so we basically, I'm struggling to fully explain this right now, but without drawing. But it's basically whether or not you want that array to live on the cells. So like your dimensionality along each axis is either n or n plus 1 for the cells or the points.
So does that mean the dimensions are always with respect to the point? Like you need an extra bit of room?
Yep. Exactly, yeah. So the dimensionality of the image data is defined by the number of points along each axis. And so if you want that numerical array that's length 20 on the x, we need 21 points on the x dimension, and same with on the y and the z. And so that's why it's this shape of that array plus 1. And that would let us put it on the cell data. If you want it on the point data, you would just leave the dimensions as the shape of the array.
Thank you.
Cool.
Excuse me. You didn't say what the kernel keeps doing.
Okay, you might be good.
This is in English section.
So welcome to the PyVista figures and visualization tutorial section. In this section, we will learn how to make a great picture with PyVista's powerful plotting tools. And making picture of data is more than just showing numbers, It's about telling a story, finding new things, and sharing information clearly. PyVista gives you easy Python tools to make everything from single 3D pictures to complex multi-view figures with advanced drawing techniques. In this session, we will cover the basic building blocks of PyVista visualization, the plotter class and mesh display options, subplotting, shading techniques, texture mapping, and even making animated GIFs. By the end, you have the tool to make pictures that not only show information but also interest your audience. At the center of the PyVista's visualization, the system, which is also called flowchart, is the plotter class. Think of it as your 3D canvas like Matplotlib's figure, but made for three-dimensional data in PyVista. And the workflow is very simple, as I plot here with Mermaid. First, create a plotter instance, and second, add meshes or other objects to it, and show the result after the end. Maybe you already noticed that this workflow, but it is important to understand this workflow again to make more beautiful figures by using PyVista. So there is a lot of options which you can make your figures more interactive and make it more interesting to your audience. Like there is an option, Windows size, which controls the resolution of your output and background to set the background color and off-screen render without showing when it is useful when you want to do it but processing it. And so let's see how Windows size affects your visualization. And you can copy paste this code and do it in the Jupyter's notebook. So if you set the background color to the pink, the mesh is like this. So the background switch to the pink from the white. And in this code, we also set the Windows size to the high resolution, so you can create a picture with high resolution. And you also have to see that there is also an option that can control the picture in add mesh method. When you set the color option, when you use the add mesh method, you can set the color of the mesh to each object. So you can try this code here. So I am setting the red in the first object and set the cool warm color in the next mesh. And the last one, I control the color limits. And sorry. I set first is the setting red, and the second is setting the cool warm color scene, and the last one is control the color limits to the 0 to 100. And And you can also set to the edge visibly if you want. When you realize how to structure the mesh, it is very useful to see the edge of the mesh. And if you want to do that, you should only set edge color black and set show edges true when you add mesh. And you can see the edges of the meshes and realize that it is organized by the triangle meshes. And you can also set opacity control by using the option of the add mesh method to know that how the 3D mesh is structured. So you can set, we can use the example data and can set the opacity to the half, to the 50%, and we can set a picture like this. And you know that it is not hidden in the inside of the structure. We can see how it is structured as a mesh. And we also structure the scene with many objects using add mesh method. As we can define add mesh method, we can use add mesh method any numbers we can, so we can generate object for using for loop and can create a scene like this. This is a scene we plotting the platonic object for each position and also add the floor and each of it. And yeah, in the code, we are making the list of the platonic solid and add mesh to the plotter object and show it in the end. So we can also make subplotting, which is also we can do in matplotlib, like like this code, and yeah, we can define the shape in one in horizontal and two in the vertical, and we can plot like this. And so we are we have a sphere plotting in the far in the left and the cube plotting in the right. And we can also move it, interact by each of it. And real power comes when comparing different ways to show the same data. Yeah. If you want to see the one 3D data with different aspects, you can see the each analysis for side to side, and you can see how it looks like in the different aspect. And if you want to create 3D meshes, you may also want to show the axis or bounds and spatial context. You can also set it to the plotter object and show it like this. Oops. Sorry. I comment out the yeah, like this. And you can see the x-axis and y-axis and z-axis, and can also show the boundary of the meshes. And also, PyVista has a feature to show 3D CG. We can create shading techniques to each meshes. So this code is showing the different shading techniques for to the one meshes, like flat shading and smooth shading and shape edges. And also we can do the physically rendering, which is used in gaming rendering. So also we can do the texture mapping to the PyVista meshes. Sorry, searching it. This is an example of the physically based rendering and texturing. And if you set the option to the add mesh method, you can create a scene like this. And, it is not interactive, but we can see that Nefertari's statue is rendering in the park, and it is rendering as a physically based rendering. So in the end, we can also create an animation of the meshes. And in this example, we are creating an animation of the meshes. We are creating a plotter and meshes and changing the point position for point position in for loop and save it to GIF file and create an animation like this. And yes, and this is the section of the figure option and the animations. Is there any question about this? So if there is no question, let's start exercise about it. The first lesson is to using add mesh method, and the second one is type of shading, and the third one is texture mapping, and the last one is creating a GIF movies. So what we want to do, you to do is to do it yourself exercise. First is display options, and second is lightning properties, and third is item writing. So we will have about 10 or 15 minutes, so please do it.
share, you know?
Okay, let me start the explanation of the solution. If you have any question, you can raise your hand and you can ask me about anything. And the first one is about the displaying options. And you know that in this option, you are using the add mesh method option. You can check the add meshes option using help function and can check the docstring which kind of what kind of option are there in this method. And if you want to show the edges, you can set the option show edges to add mesh function, and also can set colors and edge colors by using each of options. And also you can set a style of the plotting by using style option. You can plot the points style option by set it to it. And also can render point as sphere like this, and can also set a color map using CMap option. Yes, and this is a solution of the first exercise. And the next is about writing properties. And you can control the lighting by using the option of the plot method. And if you set the lightning option to false, the lightning is off and looks like this. And you can also set to a specular property by using the specular option. And if you set specular to 1, it is more like specular thus show a figure like this. The left one is no spectacular and the right one is spectacular of 1. And you can also set it more larger specular power by using specular power option. And also you can set diffuse, specular, and ambient in use together to show more like physical rendering. And the last solution, last exercise about IDOM writing. You know that IDOM writing is one of the rendering option which is used computer graphics. And if you create a point cloud and render it to PyVista, it looks like this. You know that there is no shadings and cannot recognize what kind of the shape it is. And if you set IDOM writing on, you can show like this and can recognize the shape which is created by the point cloud, and can also see the scalars of the elevation by setting like this. Yes, and the solution of the exercise is this. And any question about it? So I will continue to the next section about filters. And welcome to the PyVista's filters section. And I'm excited to guide you through one of the most powerful features of PyVista. Because in science visualization, we often work with complex 3D data sets that have more information that we can show at once. And filters are our tools for getting, changing, and highlighting the specific information we need. Think of filters as a smart data mining tools that help us find patterns and insights hidden in our 3D data. In this section, we will look at how PyVista makes these powerful operations easy through a simple Pythonic interface. So the reason we are using filters is that we can get part of data based on rules and make new quantities from existing data and creating geometric shapes, abstract data, and make complex geometries simpler for analysis. For example, if you want to get to the data from one elevation, you can use a filter, and if you want to create a simple, if you want to divide meshes from the simple meshes, you can also use a filter which is powered by the VTK. And I want to look at each of the filters. And the first filter is the slice, which makes a single flat cut through your data. And it is perfect to looking at internal structures. And the next one is threshold filters, and which keeps only cells where scalar values are within a specific ranges. And it is very useful when you want to see if you, I want to see the area which the temperature is 0 to 100, like that. And also there is a geometric filters which create a new shape, like outline corners, which is create outline of the meshes that create the shape from the edge of the geometry. And there is also analysis filters which can create glyphs from the point data, and by using it, you can create an arrow from the point data by using this filter. Okay, so let's take a look about the filter by using a code. So I am creating new notebook. Yeah, this is a code about the uniform data, and it have a filter of the. I will take a filter to this data set, and but before that, it is important to see how the data is constructed. And by checking this in this cell, it says the number of the point is 1000 and number of the cells is 7 729. And to filtering it, we can use it to threshold which get to the area which the data is 100 to 500. By running it, we can see that the original cells is 729, and after doing the threshold between 100 to 500, the cells is decreasing to 310, and it means that the percentage of the kept is 42.5%. And you can also do it by single value. Like if you want to get to the data which is equal to 300, you can threshold 300. And if you want to keep only values before 2000, not 2000, 200, you can set up a 200. Oops, sorry. This code is not correct. So this is very useful when working with a data set where you don't know the exact structure beforehand. If you set the range to the threshold percent. And after thresholding this, we can visualize how the filter is working. So in this code, we compare the two meshes. One is in the left, the data set before thresholding, and the right one is the threshold filtered data. And sorry, I maybe mistake the code. Yeah. This means that the outline is created by the original data set, and also a thresholding data set from the original data, and plotted together, and it shows that where the data set is dropped from the original data. And also, if we want to see the data set for the many aspects, we can compare the difference of each filters by using subplots. So this is, I'm using the example of the filters. Yeah. Yes, this is the code of the multiple filtering code, and in this code you can see 4 filters, and each filter is first is about the threshold, and the second one is the contour which create the edges of the value ranges, and the third one is the slices, which can create the meshes sliced by the one position, and the last one is creating the glyphs, which can create an object by the point data. And to watching the result of each filters, we can recognize how how the original data is structured. And we can filter the original data in various filters, but we can also combine them in one pipeline. This code is combining the filter in one result, and it creates pipeline which thresholds the data set and relevant data set and clip data set and slices also gonards, and it shows the result after changing it, and you can see the result of the pipeline. So, yeah, that is the explanation of the filter, and I want to do yourself by solving these exercise. One is clipping with plane and boxes, and the second one is computing surface normals, and the third is about contouring, and the last one is about plotting glyphs. So we will take about 15 minutes, so please try it.
there is something I want to like drive home about filters. So in PyVista, we can chain a lot of filters together, and so there's sort of this syntax to using filters in PyVista where it's always a mesh in and a mesh out, with the exception of like 2 cases where they return something other than a mesh. But almost always a filter is going to transform your mesh into some other mesh. And so you can say things like .threshold, .contour, .slice, and you can chain them together so that way you have this sort of pipeline of mesh objects moving through the filters. Just wanted to drive that home, that a filter is always mesh in, mesh out. And filters like slicing or contouring, they're geometry reducing. And so if you have a volume and you do a contour, it would take your volume and produce, so that's 3D geometry, and a contour of a 3D volume would be now a 2D surface. But if you have a 2D surface and you contour that again, you would get 1D lines, ISO value lines on that surface. And so you could do that, and you could chain multiple contours together to reduce it all the way down to 0, which would then give you points. I can't think of a useful reason to do that, but you can. So I just wanted to sort of drive home the nature that these filters are always transforming your data, mesh in, mesh out, always. Yeah, so Tetsu was asking, like, if when we're doing these chains of filters, what's sort of inspiring that usage? I think when I came up with this filter API, it just felt intuitive to me. I'm wondering if Pandas has an analog to this. Yeah, because I think Pandas, it has some functions I know that they just return a new copy of the data frame. It transforms the data frame in some way. You have a new data frame, and then, so that's another. Yep. Exactly, yeah. Yeah, and so I think we tried to mimic that sort of pattern, so that way it felt a little more intuitive. We could chain these operations together. But it is important, whereas like in Pandas, an operation might transform the data frame in some way and just return a reference to itself. In PyVista, our behavior is to return a new copy of your mesh, like a whole separate thing, so we're not updating the previous one. And so it's always a new copy, new mesh all together when you run a filter.
How live can you filter updates?
It's going to depend. It's going to depend mostly on your data size, and so like, do you have an example that you're thinking of?
So this example of like slicing a rabbit, you have a slider here, it's like how full do you want the rabbit to look, and with that big amount, how fast can you affect the render into that?
Yeah, I'm just going to show it. So, and we have some. This is a great question because like choosing that slice plane of where you want to clip your data set, you likely don't know initially when you're plotting, so you want to move it around in space. So we actually, it will compute those clips pretty fast, especially for that bunny mesh, but for most data sets I see people work with. We also have a way of adding a widget to the scene. And there's some tutorial content on the website. Let me plug in so you can actually see what I'm looking at. No, so we are gonna approach time in the next half hour-ish, and we're thinking basically we're gonna drive home how you can use PyVista and web apps and use a framework called Tram to deploy web apps with 3D visualization front and center. We'll sort of finish on that and then basically like just kind of run this as a workshop for the rest of like, what questions do y'all have? Do you have your own data? Let's see if we can visualize it together, that sort of stuff. But let me show you, of course, I'm gonna select this window here, cool. Okay, so let me So one thing we can do, I'm just going to do this from scratch. If so mesh equals examples download bunny, I think, bunny. And then we've got a mesh, right? And we can say PL. So we can do PL equals pd.plotter. We can create our scene. We can use a convenience method that we've added to the plotter for adding an interactive widget to the scene. So we can say add underscore mesh, but then I can tab complete. There's a few other add mesh functions, and these all have widgets associated with them. And if I do clip plane, and then it takes the same parameters as add mesh basically, but just adds a clipping plane for that mesh. And so I can say mesh here, and then pl.show. And what we get now is I have my bunny here. I can rotate my 3D scene around, and I can click the plane, and I can just move it, and there we go. And so you can choose your clip plane for your mesh. You can introspect all your data. And if I had a 3D volume, say, so the bunny is just a triangulated surface mesh. So clipping it, you don't really, you're not uncovering any new data in there. But if you had a volume, and one example is a wavelet. This is just a simple data type example in PyVista. But if we do that, so it's image data, again, it's got those 3 dimensions, so it's a whole 3D volume. And when I plot this now and I slice, I can see the data along that slice plane. And so I can move this through and see the data as I'm slicing. Yeah. Cool.
But if you want an external widget, how do you modify the current scene? Will you have to re-render it and save the current camera position and sort of pick it, or like how would you do a live edit to what the current rendering scene is? Or is it, you were doing this in Jupyter, you're executing one block of code, and you had a program that's modifying that scene, it's going to be constantly changing.
Yeah. So if like you're in a workflow now and you've found a clip plane that you want, this clipping widget is set on the plotter. And so I think what we can do is we can say pl dot, oh gosh, I'm trying to remember. It's been a while since I've done this exact thing, but we do track that origin and that normal of the widget. And you'll pull it from there. And so like what you would do, and what we often do for the camera position, for instance, is we can say pl.camera position, and like we'll just show it in the notebook output, and then copy it, and hit enter, like, or equals that now. And so now it's hard-coded. Like you found the one you like interactively, output it in the notebook cell, copy it into code now. And so then if I rerun and reinstantiate my plotter, then I can rerun this and call pl.render, and boom. And it gets set on there. And so that's one way you can interact with your data in a 3D scene, capture the state, and then put that state into code and save it.
So we call render to update your image.
Yeah, that's necessary in Jupyter notebooks. You need to call render and it will update. This is it's not supposed to need that. It's supposed to just interact, but sometimes in Jupyter you have to call render. So like if I just do this and I hit this and then I click, and as soon as I click, it's like, oh, it has some state it needs to resend. Yeah, it has to redraw. And so it's not supposed to be necessary, but let me show you. Yeah.
I never used Jupyter, I just make that.
Yeah, if you're not in Jupyter, then you shouldn't need to call render, it should just update. And there you go.
Question.
Yeah.
I just tried saying what I'm to HTML file.
Okay.
And was the rotations to work. So I found that are you using HTML?
Yeah, this is interesting. So one thing you can do, or this, if you're interacting with a scene in a notebook, let me do one that's simpler. It doesn't have a widget. So if I did the mesh equals examples dot download bunny, so I can say PL equals pv.plotter, that's standard sort of syntax we use, add mesh, add my bunny mesh, and pl.show. One thing you may have noticed if you hovered over these icons that come up in the 3D viewer is there's one over here, this last one of the download export scene as HTML. This is the same thing as calling the API pl.export HTML. But if you just click this little download button, that downloads an HTML file with your data and the scene graph embedded in it. The capabilities of the 3D rendering is not a one-to-one match of what you see because we have to export to a different rendering framework. But when I get that, and so I can now open this file, and so I have this HTML file. I guess y'all can't see my URL bar because it's cut off at the top, but it is loading that local HTML file I just downloaded. And so you can try this on some of your scenes, download them, and then you get the same scene rendered locally in your web browser. And we're using VTK.js for this. So VTK has a JavaScript flavor. It's limited in its functionality compared to the C++ version of VTK. Something that is exciting and coming in the future is that they are working diligently to take the 30-year-old VTK library built in C++ and compile it to WebAssembly such that it will render and run natively in browser. That's coming very soon. There's some working demos of this already. I don't think I could show it today because I would have to go remember how to spin it up, but it does work and coming soon. And so that would have then the one-to-one match. And so very often, like some of the more advanced rendering techniques we expose in PyVista that's available from VTK, it won't export in this HTML format because VTK JavaScript flavor doesn't support some of those techniques. But once VTK compiles the WASM and they bundle all this up nicely, we'll swap that out and we'll start using that. And so then there'd be a one-to-one match, save your scene graph, load it in browser, and it all just renders natively in your browser. Yeah, that's on the horizon. Exciting things to be excited about in the future. Okay. Has everyone had a chance to sort of sift through those example exercises? See some nodding heads. Yeah, cool. So we're going to end at 5, which gives us 30 minutes. I figured for the rest of the session, we could kind of just more of workshop style. I'd love to hear, like, throw your questions at me and Tetsu as well. And we're here to answer your questions. We're also here if you have some example data and you want to plot it, we're here to help you do that. We'll answer a bunch of questions. I will maybe just do a really quick overview of this tram section at the end of the tutorial. So I don't want to do a complete deep dive into this, but more of like, it's a teaser. If you're interested, go toy around with this. So tram is a web framework for building web application, like single page web applications in pure Python. It uses Vuetify for all the UI elements. It's all configurable in Python. However, it's made by Kitware, same people who make VTK. And so it has really excellent support for 3D visualization in PyVista. There's a number of examples in here that go through and show how to create a few really simple tram applications. And what we can do is, I'm going to go to one of them. Let me scroll down to, is it this scalar range? I forget which one, but I'm going to run it in the notebook with you all and show you. So copy this, go here. Okay. And what we're looking at here is effectively, so Tram's really nice because it's meant to build standalone single applications that run like on a web server and produce a web page that people can go visit. But you can also run it in a Jupyter Notebook and see the web page in a Jupyter Notebook output. And so that's what we do here. I'm not going to really explain the code too much because Tram has its own sort of syntax to it and how you define UI elements and all of that. But what this code snippet does is it creates one of these apps with a PyVista plotter, and we have this little scalar, this little slider here to control how we're doing the color mapping with PyVista, and so we can use UI elements to drive the state of PyVista's visualization, move things around, all of that. And so like what we see in this notebook output is just a single page standalone web application, and so you could make very sophisticated web apps with 3D visualization front and center, and use Tram to help just manage that state and wrap all this up in a clean way. And so Tram, it's really easy to use. It's pretty beginner friendly. And so I really recommend perhaps reading through some of that section on our tutorial website, playing around with some of those examples and seeing if you're interested in that. Very akin to, if you like Streamlit, those sorts of things, it's similar but quite different from those. It's more similar in spirit to things like Streamlit, but quite different on a technical level. Cool. So I think we're gonna call it on tutorial content at that point and say like, we are here to answer questions, help you code, help you look at data you're interested in. If there's like, you feel like we didn't explain something thoroughly enough, I'm happy to go back through or point you all to sections in the PyVista documentation. Cool.
I also want to know what kind of inspiration you have when you use PyVista in a
Yeah, does anyone here want to take immediate action and start using PyVista with their own data? Few people are, yes. You don't all have to be excited, it's okay. I want to know what domain are you in and what kind of data are you dealing with?
Well, if you think about the model analysis data, so shape testing stuff, you can have some ways that you put a shape on and have libraries to do mode shapes. So that's got a lot of visualization aspect to it, looking at the meshes where you put accelerometers and how much amplitude you're seeing. So there are tools out there, professional packages that show you animations of mesh stuff like that. Yeah. So we can look at that and we can look on it.
Yeah, super cool. I will encourage you to go look at, there's a section in the website, PyVista in Action, and it's all about different community projects. So people in their own engineering science domain using PyVista as a supporting library. And I'm not sure if I drove this home. Alex and I, when we set out with PyVista, we really focused on building it as a supporting library for us as developers of other platforms and other toolkits. And so Alex and I collectively have built, tens of different desktop applications or web applications where we're doing some sort of analysis, whether we're doing subsurface analysis and looking at models in the subsurface, or Alex is in aerospace engineering and looking at how, the structure of turbines and jet engines and things like that, and performing analysis routines on that. I've worked with other people where they're trying to resolve differences between their CAD models and like high resolution LiDAR scans of the actual manufactured products. And so we built PyVista as a supporting library to give us all the tools we need when we go in to solve these very specific domain problems. And so I want to encourage, if there are developers here who want 3D visualization as a part of their own platform, that's what PyVista was built for. Sure. And I'll let Tetsu show.
Maybe this is what you want to have. This is a model analysis pump bracket example. And it shows the model analysis result, and it is a result before it is deformed, and the result is after default, and you can also show the animation of the model. Yeah. My domain is also about the this kind of the analysis. So yeah, I'm familiar with your purpose.
There's like people from all kinds of ways who work in PyVista, so go check out our documentation in addition to the tutorial website. Search on our GitHub discussions, there's a lot of activity there. And I'm often surprised at this company. They're very nice folks who are this long. So if you have something, just Google PyVista. Hopefully something comes up. If not, please engage on our GitHub discussions. This is an old thread on our GitHub discussion extensions scrolling through. We to it. It should be pinned if you go to our GitHub discussions where you basically just ask, who are you and how are you using PyVista? And a lot of different people try to from all kinds of areas. Use PyVista in their research or engineering research. So it's kind of fun to do through this. Curious, are there any other geoscientists in the room?
Whether in mind.
Accounts. I'm curious where like other people are coming from.
I'm a biologist, this isn't relevant to my work now.
Yeah, I've done a lot of large analysis and constantly stuff in Massachusetts, 2D visualization. Yeah, I have to do 3D stuff, reacting structures, 3D sort of slices and evolves it now.
Maybe it is more similar to IT.
Yeah. You can. And like, one example, I did an X-ray of a heart recently, and so the hospital gave me DICOM images. They're a bunch of 2D slices of the X-ray, right? And I could go and I stitch those together as just on the z-axis of my image data. Each z slice is just a dimension. That interpolation, like whether or not that's realistic, probably not. But like it did a great job. And so just like yeah, if you make a 3D numpy array of it, just pass it to PyVista. And actually, I didn't show this, I'll show you on the part where you create some of these data structures. There's a PyVista.wrap, W-R-A-P, and you just pass a 3D numpy array to that. It was that concept of the partial size. close enough together. Some of them are the headphones, MRI, raw, X-ray, every day. So,
Yeah. Yeah, but when I had mine, it was a CT scan, so it was X-rays. Yeah, and those were just 2D slices where the X-ray went through me and created slices, and then I stitched them together. I probably have that data set somewhere on my computer I can dig up. It's cool. It looks, yeah, it's like dealing with that data is actually really hard, and some of the visualizations, they look interesting, but they're kind of spooky looking. Yeah, and that's one of the problems is like once you get into some domain, whether it's medical imaging or something else, like there's all kinds of proper analysis you have to do, like smoothing on, yeah, and so like, yeah, knowing exactly how to smooth it, and this is where like we have the filters for all these things in PyVista, but then fine-tuning the parameters for what it makes sense in your domain is sort of the challenging part. Yeah. But I really want to encourage everybody to go to the main PyVista documentation website, and there's an examples gallery, and I think that one's a lot more comprehensive even than our tutorial. It shows different domains people are using it in, all kinds of common tasks. And everyone got a sticker, right? Raise your hand if you want one and you didn't. Okay.
Yeah, and for new documentation, we allocate level for each data set. So if you want to find some kind of medical data set, you can set, you can click and go to the data set which is labeled.
Actually, I think this is relevant for everyone. So you're asking about like I guess my journey from scientist to software engineer, and getting involved in open source. So for me, like it started when I was in grad school, and I just needed tools to do the research I was doing. There just stuff wasn't working, and so I just started coding it up in Python. And it started as dirty and gross as it gets, of like, I just had a bunch of random scripts and I'm uploading them to GitHub, and it really, I just strongly advocate to learn by doing. Just go start doing it, and I think because I was willing to put like the ugliest, grossest code I've ever written on GitHub and let other people look at it and be like, oh, that's useful, that's really where I started to learn and became a better software developer because I was engaging with other people who were much smarter than me. And like, I think contributing to open source turbocharged my own career just because I was getting code reviews from people who had 20 years of engineering experience on me, and people who needed, but they didn't know the thing about 3D visualization that I happened to know, even though I wasn't good at coding. So I just advocate, like, just go engage the open source community, especially on GitHub's really warm, friendly, and accepting. And even if you think your code isn't good enough, it's just fine, and people will help you make it what it needs to be. I'm curious if you have any other questions on that. Yeah, so VTK is written in C++. In itself, it has Python bindings. And so VTK, written in C++, you can pip install it with its Python bindings, and you're effectively just using the C++ API directly through Python. And so PyVista is written entirely in pure Python, just wrapping those bindings again. So it's like wrapping a wrapper. And so yeah, it is pure Python. But we do a lot of clever things. Yeah, it's further abstracting the wrapper, yeah. Yeah.